All right, now we're going to talk about Chapter 21, Circuits and DC Instruments, Resistors in Series and Parallel, EMF, and Kirchhoff's Rules. Resistors in series and parallel, the big difference is the way they are hooked up. This is series, that's parallel. What's the difference? If I'm an electron, I've only got one path, and it's through all these resistors. But if I'm an electron in this circuit, then I get to choose. I can go through that resistor, or this one, or that one, or this one, and then get back up with my pals down here on the other side. So in parallel, current can flow around the resistors and take different paths. So the way the current works in there is a little bit different. In series, the current's constant throughout the whole thing. Okay, so resistors in series. The main goal in this section, what you're going to be doing with circuits, is turning a circuit with 1, 2, 3 components and simplifying it down to one single circuit with one power source, one current, and one resistor. So you can do V total equals I total times R total. Once you have that, you're good to go. So the main thing you're going to be trying to do in these in this chapter is turn a circuit with multiple components, figure out how to combine them into a circuit that only has one component. So we can use V equals IR for the whole thing. All right, so in series, the voltage from the battery is equal to the voltage across each of the components. So the voltage here, V1, V2, V3, has to add up to be the voltage here. And that's what this is about. Now you know that V1 is equal to IR1, and V2 is IR2, and so on. So you can plug that in here, and then since the current is constant, factor that out, and then you get I times R, plus 1, plus R, plus 2, plus R, plus 3. So you end up with V equals IR, where R sub S here is resistors, the equivalent resistance in series, and that just turns out to be R1 plus R2 plus R3. So if we go up to here, and you have a resistor R1, R2, and R3, and you want to simplify into this circuit, well, RS here, that just equals R1 plus R2 plus R3. You just add them up. Okay, so it becomes very simple. So for example, you've got a 1 ohm, a 6 ohm, and a 13 ohm resistor here. Well, you want to figure out what is the total resistance. That's easy, they're in series. You just add them up, 20 ohms. For B, what's the current? Well, it's just V over R. 12 volts over 20 ohms, 0.6 amps through each of these. Every resistor here, 1, 2, 3, all has the same current. And you can think about that in terms of conservation of charge. All right, for C, the question is, what's the voltage drop across each resistor? Okay, well, we know the current is constant. Sorry, not there. The current is constant, 0.6 amps, 0.6 amps, 0.6 amps through each of them. So if we want to calculate the voltage through each of them, it's just going to be the current times the resistor. V is IR, IR, IR for each of the resistors. So we get a 0.6, 3.6, 7.8 volt here. So the total voltage then is just V1 plus V2 plus V3. And plug those in, and that adds back up to 12. So basically we've got our circuit here, and we're starting with 12 volts. And then we have, whatever, 0.6, 3.6. So we've got 0.6 volts here, 3.6 here, and 7.8 here, whatever that is. So voltage drop there, voltage drop here, voltage here. So you start at 12, drop down by 0.6, drop down by another 3.6, drop down by 7.8, and back to 0. So you get 0 on this side of the battery, 12 up there, and you're just starting uphill. And then with each resistor, you're going downhill a little bit, changing your potential. All right, and then D was what's the power in each of these circuits. So now we have V equals IR. We could figure out the power anyway. We've got the current, we've got the resistor, and so we've got that voltage, we've got all three. We could do I squared R, we could do V squared over R, we could do P is IV, and just do current times voltage. Whatever you want to do to figure out, you should get 0.36 watts or 2.16 watts or 4.68 watts for each of these, depending on either using P equals IV or P equals V squared over R. And you should go ahead and just test that and just make sure that's correct. E is find the power output of the source. Okay, so the power output of the source is just 7.2 watts. And so if you add each of those things up, you get that, which they're showing here. And so the total power is just the total current times the total voltage. So the current coming out of the battery and the voltage coming out of the battery. Okay, so here's your main features. Series add up. If resistors are in series, just add them up to get your total resistance. The second thing that's really important is the same current flows through each of the resistors. That's because they're in series. They have to have the same current. Individual resistors in series do not get the voltage source voltage, but they're called voltage dividers. They take some of the voltage out of it. Okay, so they don't take all of the voltage, they take some of the voltage. So you got a 12-volt battery. We didn't have 12 volts on any one resistor. We had 3.6, 7.8, and so on. All right, so now let's look at parallel circuits. So now we've got resistors in parallel, and again, what that means is that their ends are all ganged together. Bing, and all ends are connected by the same wire, okay, versus having them all go through the same current. Okay, so in the case of here, your current from the battery, you're still going to have I total and V total, but now you can think of this top up here as V and this down here as 0. So every one of these resistors has the same voltage, V, V, V at the top, pushing down. Okay, they're all at the same potential to start with. Okay, so they all have the constant V. But since current has to be conserved, some current goes here, some gets split off. That means R1 is going to have different current from R2, and then it's going to get split again, and like that. So our current that starts at I total is going to be, when we try to simplify it down over here, the way that resistors add up and the way the current behaves is different from the resistors in series. So for resistors in parallel, the total current out of the battery gets split up, and you've got I1 and I2 and I3 through each R1 and R2 and R3. So if you do V equals IR, and then replace I1 with V over R1, V over R2, V over R3, you see that your total resistance in parallel is 1 over R1 plus 1 over R2 plus 1 over R3. And so that's your, if you want to calculate the total resistance of your circuit in parallel, you just add up the resistors in parallel. So let's do our same circuit that we had before with 1, 6, and 13 ohms, but instead of being in series, we've got 1 ohm, 6 ohms, and 13 ohms here. And if you do each of those things and calculate what they should be, we have to add up to get, again, the same strategy. We're just trying to simplify the circuit so we can do V total equals I total times R total. Okay, and once you do that, it makes it easy to figure out the rest of the circuit. So our first step then is to figure out the net resistance, the total resistance. So we're going to have 1 over 1 plus 1 over 6 plus 1 over 13, and that's going to give us a number. And what is this? I just want a new note. Yeah, okay. 1 ohm, 6 ohm, 13 ohm, okay? And when you do that, you get this 1.2436, but that's the inverse of what we want. We want to do 1 over that, and so solving for that gives us a net of 0.8041 ohms. Okay, so that's lower than any individual resistor, and that's the cool thing about circuits in parallel is that, circuits in parallel, the current, you get 3 times the flow. So even though each resistor is here, the total current through the, the resistance is actually lower overall than if they're in series, because you've got more paths for current to flow. So it's like opening up 2 more checkout lanes in the store. So that's one of your tests for when you're calculating this stuff. Your resistors in parallel should be less when you add them all up than any of the individual resistors. Okay, so as predicted, RP is less than the smallest individual resistance. Then you can get the total current, 12 volts over that. So we got way more current in this circuit when those resistors are in parallel. Okay, so part C wants to know, calculate the currents in each resistor. Okay, so we just do what each one is using constant voltage. Remember, they're all at the same voltage, so that doesn't change. 12 volts, 12 volts, 12 volts. We get 12 amps, 2 amps, and 0.92 amps. So the resistor with the lowest resistance has the highest current, which makes sense. The next and the next are the next and next lowest currents. So the one with the biggest resistance has the least current. And that makes sense. Which path are you going to take when you go to the checkout line? The one where there's only one person waiting, or the one where there's 10? Okay, so if we add those three currents back up, boom, we get our total current, and that makes sense. Power, use the same equations, whichever ones you want to do, since we know everything, and you can get the different amounts of power being emanated by each of these components. Okay, blah, 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 bloody, bloody, blah. So, major features. The reciprocals add up, okay, and the reciprocal is smaller than any of the total resistance in parallel is smaller than any individual resistance. Each resistor in parallel gets the same voltage, okay, but the current, they don't get the total current, they divide the current up. Okay, so the current going through the resistors in parallel are not the same. So we've got an example of a more complicated circuit here, and the strategy is we recognize, oh, those three are in parallel. So if I want to calculate RP, I'm going to say 1 over RP is equal to 1 over R2 plus 1 over R3 plus 1 over R4. I can figure out what that is, and that becomes this whole block of text becomes boom, that resistor. And then we say, okay, these two are in parallel. Let's combine them the same way. 1 over R5 plus 1 over R6. And 1 over that is going to be this RP prime right there. Okay, so now we've simplified the circuit quite a bit because we've figured out the resistance of these three. We combine them and those two and combine them into this whole circuit. But then these two are in series, so just add them up. So this is going to be RP plus RP prime, the way they wrote it, and boom, it becomes RP double prime here. But then these two are in parallel, so let's simplify the circuit even more. Boom, these two are in series, and then add them up, and here we go. We've got our final case where we've got one voltage, one resistor, and we can say the total current is equal to V over R total, V total, okay? And that way you can calculate the current through the whole circuit. And then now you know the total current coming into this resistor. You know the total current is going to hit there, and some is going to be split here, and some is going to be split there, and then it's going to be split into 3 ways here, and then when it gets here, it's going to be split into 2 ways, and then, but you know, when it comes out of the bottom here, it's going to be the same here as it is right there, and then when it recombines down here, this is going to be the same as V total. But how you would do it, if I were you, delete all this. So let's say I'm trying to figure out the current in each of these components. So I figured out the total current, and then what I'd have to do is step back. So now I'd go to this one and work backwards. So I've got the same voltage, same current, but now I can find V1 and V2 at each of these points. And now I've got V1 here, and I know that at V2 across these two guys is the same because of this situation here. So then I can calculate what I1 and I2 are, at least in these resistors, and then I can work back up to here and say, okay, well, V2 and V2 are the same. They have the same voltage here because of our previous problem. And then let's see, yeah, and this one is also V2 there, but we're not going to worry about that. And then you can calculate the current through this zone, and then you work backwards even more and get what this V is, because you know that the V total is equal to this V plus these two V's, and then you can get all the way back here, and at that point you've figured out what each of the components are. So that's really tedious, and that's really kind of annoying, so I don't think we have to do any of that, but that's how you would do a problem like that. You simplify all the way down and then work back with each step to figure out the V's and I's in any case. Okay, so let's say we've combined a series and parallel circuit like in this example here, and we want to figure out the total resistance. Okay, this is easy. We've got R1 here, so our total resistance is going to be R1 plus R parallel. And what we have to do is combine these two resistors together in order to get R parallel. So R parallel is going to be equal to, I'm just going to give you this formula, R2, R3 over R2 plus R3. This is the same as doing 1 over R2 plus 1 over R3, because if you multiply top and bottom by R3, you get R, well, if you multiply both sides by R3, okay, then that goes away, and then multiply both sides by R2, and R2, okay, and then that cancels out this one, so then you have R3 plus R3, R2, and, oh, what am I doing? I screwed something up. Sorry, I'm being distracted. Okay, so, okay, sorry. 1 over R2 plus 1 over R3. So if you get them, you need to do a common denominator. So R3, R3, R2, R2, and now you have R3 plus R2 over R3 times R2, and then that equals 1 over R total. So if you do 1 over that, then you get this formula that I was trying to show you, which is R2 R3 over R2 plus R3. So if you have this situation where two resistors are in parallel, so it looks like this, this is one thing you can memorize so that you can get your result faster for resistors in parallel. Otherwise, you calculate what it is down here by doing the old-fashioned way. Okay, but once you do that, R1 plus R2, so this is, since these two areas are in series, you can just take R1 and then add in these other things. Okay, so once you do that, you find your total resistance. So that's part A. What is the total resistance? It's just the sum of 1 ohm plus the reduced resistance of these two, and you have to figure that out. So you get you can get your reduced right here. So you get 4.11 ohms is the net resistance through this part of the circuit, and then you just add 1 ohm to that because they're in series. So you get 5.11 ohms for your total resistance. For B, what is the voltage drop? V equals IR. So what's the voltage drop in R1? Okay, now that we have the total resistance, we can figure out the total current. So we have to figure out the total current first. So we can solve for I, and we get 2.35 amps. That's the current coming out of the battery, 2.35 amps. Then we can do V equals IR with our 2.35 amps. So we've got 1 ohm resistor, so we have 2.35 volts there. Okay, so that's how you figure out V1. And then C, what about R2, and then what's the power? So to get through I2, we know that there's 12 volts off the battery, and then we know that there's 2.35 volts off this resistor, which means that coming into here for both of these resistors, since they're in parallel, they're in the same voltage of 9.65 volts, which is 12 minus 2.35. That's the voltage that's remaining. So we got 9.65 volts there. So we can do that over R2, get the current there, do the same voltage over R3 if we want to get the current through R3. And then for power, I squared R gives us our 15.5 volts, okay? So, or watts, sorry. And that's how you do that problem. Okay, so electromotive force. So if you forget to turn off your lights, they slowly dim as the battery runs down. Why don't they simply blink off when the battery's gone? Their gradual dimming implies that the battery output voltage decreases as the battery is depleted. Furthermore, if you connect an excess number of 12 volts lights in parallel with a car battery, they will dim even when the battery is fresh and even if the wires have very low resistance. This implies that the battery's output voltage is reduced by the overload. Okay, this is an interesting thing. The reason for the decrease in output and voltage is depleted is overload is because the voltage sources have two fundamental parts: a source of electrical energy and an internal resistance. So here's an important point. So for the electromotive force, you can think of batteries as a source of energy, but there's different types of generators, solar cells, and all these things generating voltage using a potential difference. Okay, any device that's generating power has a potential difference and can supply a current if it's connected to a resistance. So if you have a battery and you hook a resistor to it, boom, you have a circuit. This is going to, current is going to flow around this loop, okay? But on a small scale, the potential difference creates an electric field that exerts a force on the charges, which causes the current. This is the electromotive force, and it's called EMF. It's not a force, it's just another type of potential, okay? So EMF is the potential difference of a source when no current is flowing, okay? So if you just have a source set up, you're generating an electric field by the nature of your potential, and you don't necessarily have current flowing, but you have an electric field generating that's pushing on the current, and that's called an EMF. It's directly related to the source of the potential, such as the chemicals in a battery or whatever, but it differs from the voltage output when the current starts to flow. Voltage across terminals of a battery is less than the EMF when the battery supplies the current, okay, and it declines as the battery is depleted, or if you put too many things on it. But if the battery's output voltage, if the device's output voltage can be measured without drawing a current, then the output voltage will equal the EMF even for a very depleted battery. Okay, so this is a little bit tricky thing. But if you have a battery here, right, and you're trying to measure the voltage across the battery using some sort of probe, then the voltage that you measure is going to be the EMF minus the current times the resistor, or the voltage drop across your little resistor here. So let me erase this. Blah, blah, blah. Okay, so this schematic is representing two fundamental parts of any voltage source. The EMF and internal resistance here are in series. The smaller the internal resistance for a given EMF, the more current and the more power that the source can supply. All right, so V equals EMF minus IR, and what you're trying to do when you're making a battery is to reduce the IR as much as possible so that the voltage is equal to the EMF, okay? The lower the internal resistance, the better the battery source. Let's look through here, so yeah, we can explain or ignore all that. So what you really care about here is this terminal voltage V, and the terminal voltage is is EMF minus the internal resistance, okay? And this is a little bit in the weeds and stuff because we usually ignore this and just say the total voltage is 12 volts, and we're assuming that the EMF is equal to the EMF minus the resistance is equal to the voltage. But okay, so let's look at this. A certain battery has a 12 volt EMF but an internal resistance of 0.1 ohms, okay? Calculate its terminal voltage when connected to a 10 ohm resistor or load. Okay, so what we do is we say, okay, we want to know what is the terminal voltage when it's connected to a 10 ohm load. So the first thing we're going to do is we've got a 12 volt EMF. We're going to divide by 10.1 ohms because our load is 10 ohms and our internal resistance is 0.1 ohms. So we should measure 1.188 amps. If we plug that back into here, then we take our 12 volts minus our IR, our internal resistance times the current, and we get that the voltage we measure on the battery is 11.9 volts. So if your battery says 12 volt rating and you put your probe on it and it says 11.9 volts, don't be mad. That's just because you're measuring the terminal voltage, which includes the internal resistance. Okay, so anyway, continuing on, there's a couple more examples here. You can calculate the power, calculate the voltage, and so on. Okay, yada, yada, yada. So multiple voltage sources. You could have your internal resistance and your internal resistance. And this is just showing you what this battery looks like if you got two cells stacked together, and you just add them up. And you can just add them up in series. Voltage 1 plus voltage 2 over R1 plus R2, and then you add your load in there too if you want to calculate what your total EMF is. Okay, so, and same thing here. I don't know why you do this, but you've got two batteries hooked up, and you can get the current flowing in this circuit. And then we've got two batteries. This is how normally when you put batteries in a remote control or any sort of device, you stack them up back to back, and that's to double up their EMF. And so you just do EMF1 plus EMF2 divided by the total internal resistance plus the load, and then you can get the current on it. So there's two types of problems, ones that are looking at the EMF question, and so you do this type of strategy when you're calculating the total current or whatever. For most other circuit problems, you just assume that the EMF and the terminal voltage are the same, so then you don't have to calculate what this is, and then you just assume that it's 12 volts over your load of whatever it is, and then you don't have to add in your internal resistance. So when you're doing physics problems, just be cognizant of usually you'll focus on one or the other and not have to worry about both. Okay, so yeah, animals as electrical detectors. Okay, here's a shark for some reason, a sand tiger shark. They've got electroreceptors in their snouts to locate prey. We've got solar cells for power from the sun. Okay, and then the last section here is on Kirchhoff's rules. So Kirchhoff's rules, there's two rules, junction rule and loop rule. Junction rule says the current flowing into a junction gets split, okay, and the current leaving the junction equals the current coming into the junction. So if I had I1, I1, I3, and I2, let's say, I1 is equal to I2 plus I3 because of conservation of charge, okay? So Kirchhoff's loop rule says, junction rule says the current at any junction adds up. The loop rule says that as you go around a single closed loop, so that's a loop, all the way around is a loop, that's a loop, okay? Those are all loops. As you go around a loop, the voltage drops all add up to 0. So that would mean that the E1 minus R1I, right? And then whatever the current here is, well, I'll just call this V. Okay, so call that V1. V1 minus V2 minus V3 equals 0, where that's V1, that's V2, V3. Those voltage drops all add up to 0. So you're starting with some voltage here, drop, drop, drop. It better be 0 as it's coming back into the... so these are all based on conservation rules, and has to be that way. Okay, so those are the two rules, junction rule and loop rule. And you use those two to solve whatever circuit you want. And here's an example of it. You've got 11 amps coming in here. If you know that there's 7 amps here, then you don't even have to measure this. You know that it's 4 amps because of conservation of charge. Okay, so the second rule, the loop rule, says it's a conservation of energy, and it says that the voltage drops across each of these areas has to be equal to as you go around the loop, every voltage drop equals the total EMF you have. So you're starting with 18 volts here, you're dropping, you're losing a volt across here, you're losing 12 volts across there, you're losing 5 volts across here. So 1 plus 6 is 7 plus, 1 plus 12 is 13 plus 5 is 18. Yep. So you get to 18 volts, which is what you're starting with. Okay, and that's the loop rule. As you go around this loop, all these voltage drops add up. And so what they're showing you is your battery puts you at a higher potential. You go down a little bit because of 1 volt, and you're at the same potential all the way around. Oh, another resistor, go down another, and then down, and then you're back at 0. Okay, so that's what these two rules are, junction rule and loop rule. Okay, so it's really important that you're really careful about the direction of the arrows that you're drawing, because that's how you know whether to add I1 to I2 or I3 or whatever. So when applying Kirchhoff's first rule, the junction rule, you have to label each current in each branch and decide in what direction it is going. So that's the most important thing. In figure 21.21, 21.22, and 21.23, currents are labeled I1, I2, I3, and I, and arrows indicate the directions. So if we go up here, 21.12, so here we've got the current going around, we've got 2 amps, 21.22, we've already got our arrows labeled here, and I don't think there's anything in 21.21, what did they say? 21.21. 21.21. That's BS. There's no arrows here, right? So that's a mistake. I should email them. Okay, currents are labeled I1, I2, I3, and I indicates the arrow. Okay. There's no risk here for you choosing the wrong direction. The current will be of the correct magnitude, but negative. So if you choose the wrong direction, you just, add it up and you solve for a negative number. You go, oops, okay. So when applying Kirchhoff's second rule, the loop rule, you must identify a closed loop and decide which direction to go around it, clockwise or counterclockwise. 21.23, yep, we're going around that way. The loop was traversed in the same direction as the current, which is clockwise. No risk. Going around the other way, you just get a minus sign. Okay, blah, blah, blah. Okay, so 21.24, that's this figure. Help you get the plus sign or minus signs right. Note that the resistors, EMFs, are traversed from going from point A to point B. So we draw a current that way. And so if you do VB minus VA, you get minus IR. If you put the arrow in the opposite direction, you have VB minus VA, you get plus IR. Okay, it's no big deal as long as you keep your signs right when you're doing your calculations. So again, if you've got a minus and a plus here, you get a plus EMF. If you do a plus and a minus, you get a minus EMF. So the signs are all okay. They work out as long as you're consistent. Blah, blah, blah. Here's some rules here. And here's an example. Find the currents flowing in the circuit in figure 21.25. So we've got two batteries here, okay? And our voltage is going to, by, rule, we take the current to go from the positive side to the negative side. And same thing from the positive side to the negative side of the battery. So we assume the directions of the currents are. And so since the current is coming in this way and that way, then we assume the current must be going that way here. And the same thing, I1 coming out of there, going back up, going back down. Okay, so then what you do is you figure out your total currents in these points, your total voltages, your total things, just like you would a normal circuit, but they're trying to trip you up by adding a couple of voltage drops here. So now we've got an 18-volt battery and a 45-volt battery, and they're working together. So the key is that we got to just do our loop rule. So our first loop here, right, we can do I2, R2. So where do we have I2, R2? Okay, so we're coming up I2, R2 around here. So we're going from point A, I guess, and we're going up I2 into our battery. So we have a I2, R2, that's one voltage drop, and then we have our plus 18 volts there, and then we have I2 on R1, and then we're back at E, and then we come back around, we've got I1 times R1, oops, and then we come back to our loop rule. Okay, so those are around that loop, all of the, starting at point A, we've got I2 times R2, and then plus 18 volts, and then minus R1, I2, and then it splits here into I1, and so then we have I1, R1, and that's our loop. So the voltage here, plus this one, minus this one, all adds up into 0. You could very easily have started at the battery, which is how I would do it. So plus 18 volts, minus I2, R1, minus R1, I1, minus I2, R2, and then back to 0, and that equals 0. So there's your simplification here. And you can substitute, and then do some algebra, and blah, 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 blah. So you get I2 in terms of I1, great, not super helpful. Now you do the other loop rule, go around, and you can get what I3 is, put them together, and then you can solve for what I1 is, plug that back in, get what I2 is, and blah, 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 solve for everything. Okay, and then if you add them all up, I3 plus I2 plus I1, then you get your total current back into the thing in the A, B, C, D, E, F, G, H, A loop. Okay, so problem solving techniques, read those. But that's the main thing with all of Kirchhoff's laws, is just label everything, get your arrows right, do a couple loop rules, and then don't forget that loop rule, and solve for all the unknowns you need. Okay, bye.